Good morning, students. In this video today I'll discuss about chemical equilibrium. So what is chemical equilibrium? Chemical equilibrium is the balance in a chemical process, in a reversible chemical process. Suppose A to B is a reversible chemical reaction. When the equilibrium is reached, you will see that there will be no change in concentration of reactant and product, reactant A and product B. Okay, that is, at equilibrium state, the concentration of reactant and product and their physical properties like their color, their pressure, all these quantities will become constant at equilibrium. And it is equilibrium. So equilibrium is a process. It is how it is actually a balance between two dynamic process. Okay, it is a balance between two moving process. Okay, and it is at equilibrium, concentration of reactant product and their physical properties like color, their pressure, all these physical properties will become constant. Equilibrium is found in both physical and in chemical process. Okay, so equilibrium is a state in a dynamic process, and it is reached at a constant temperature, at a constant pressure. Okay, that is at a fixed external condition equilibrium is formed. Now see a chemical equilibrium. Yeah, characteristic of chemical equilibrium is given. Okay, characteristics of chemical equilibrium. I have told that chemical equilibrium is formed. Chemical equilibrium, it is formed actually in reversible chemical reaction. Reversible chemical reaction. Irreversible chemical reaction do not form any equilibrium. Okay, so it is found in reversible chemical equation. Now see characteristic of equilibrium state. What are the characteristic of equilibrium state? First character is given: chemical equilibrium is dynamic in nature, that is moving. In reversible chemical reaction, I have told that two reactions are there. One reactant to product, this is known as forward reaction, and product to reactant, this is known as backward reaction. Uh, okay, so when the chemical reaction reached at equilibrium, both forward reaction and backward reaction take place simultaneously, and the rate become equal. Rate of forward and backward reaction both become equal. Okay, and this is equilibrium state for the reversible chemical reaction. When equilibrium is formed in a reversible chemical reaction, the rate of forward and backward reaction become equal. Okay, but they are moving. Okay, the reaction is not stop, it is moving at equilibrium also. Okay, so chemical equilibrium is a dynamic nature. Chemical equilibrium is dynamic in nature. The chemical equilibrium is the result of two equal but opposite processes occurring in forward occurring in the forward and reverse direction, and there is no net change occurring in the system. Okay. Due to equal rate of forward and backward reaction, there will be no net change occurring in the system at equilibrium. Second characteristic of equilibrium is equilibrium can be attained from either side, from front side or from back side also. Okay, so the same equilibrium state of equilibrium, the same state of equilibrium can be obtained from both side. Okay, that is from reactant side and from the product side also. For example, here one chemical equation is given: decomposition of N2O4, N2O4 to NO2. This is a reversible reaction. N2O4, reversible arrow to NO2 gas. This equilibrium can be obtained from both sides. From if you heat N2O4, you will get this equilibrium, or if you cool NO2 gases to some NO2 gases, then you will see that this equilibrium will form. Okay. So equilibrium can be obtained from both side, from reactant side, from product side also. Okay, and next characteristic of chemical equilibrium: equilibrium can be obtained only in closed system, not in open system. equilibrium will not form in open system. Okay, it is only obtained in closed system. So equilibrium can be attained only if the substance among reactant and product is allowed to escape. That is, the system is closed one. Okay, so equilibrium can be attained only if no substances among reactant and product is allowed to escape. That is, system is closed. Uh, Any system consisting of gaseous phase or volatile liquids must kept in closed container. If the gaseous reactant or product is removed from the container, closed container, then equilibrium will not form. That is why closed container you have to take. Okay, for equilibrium to attain. In open containers, same chemical reaction become irreversible. But in closed container, this reaction will be reversible reaction, and equilibrium will form at equilibrium will form. Next, catalyst. Effect of catalyst on chemical equilibrium. Catalyst cannot change the equilibrium state. Addition of catalyst speed up the forward and backward reaction by the same extent. Okay, a catalyst, addition of catalyst speed up the forward and backward reaction by uh, same extent and help in the attaining the equilibrium faster. In presence of catalyst, the equilibrium reach faster. Okay. However, the equilibrium concentration of reactant and product are not affected in any manner in presence of catalyst. Catalyst in presence of catalyst do not change the equilibrium constant. Okay, but in presence of catalyst, the equilibrium reach faster. So the catalyst has no effect on chemical equilibrium. So, so these are the characteristic of chemical equilibrium. Now see, law of equilibrium and concentration. Concentration, law of equilibrium and concentration and equilibrium constant. Every chemical reaction every reversible chemical reaction at equilibrium is uh, is expressed by some equilibrium constant. Okay, so equilibrium is measured in terms of equilibrium constant Kc or Kp. These are equilibrium constant. Okay, so for every chemical reaction at equilibrium, some equilibrium constant is there. For example, for this reaction H2 plus I2 reversible at 2Ha. This reversible chemical equation at equilibrium, the equilibrium constant Kc, you can uh, you can write the formula of equilibrium constant using, like, Kc is equal to root over Kc is equal to concentration of Hi, that is within square bracket Hi means concentration of Hi square divided by concentration of H2 within square bracket H2 within square bracket I2, that is concentration of H2 and concentration of I2. Okay, this is the formula of expressing equilibrium constant. For each chemical reaction at equilibrium has some equilibrium constant. Okay, so, and the equilibrium state is measured in terms of equilibrium constant. Remember that. So for each chemical reaction at equilibrium has some equilibrium constant value. Okay, and it is the ratio of equilibrium concentration of product divided by equilibrium concentration of reactant. So for general reaction, reversible, small a capital A plus small b capital B implies small c capital C. For this reaction, the equilibrium constant, you can express the equilibrium constant Kc is equal to concentration of C to the power small c. Well, you have to give the balancing coefficient as a power. Concentration of D to the power small d by concentration of A to the power small a and concentration of B to the power small b. Okay, this is the method of expressing equilibrium constant for a reversible chemical reaction. Okay, this is given. If the reactant and product are gaseous, then you can write the expression for equilibrium constant like Kp. When the gaseous reactant and products are gaseous, we can express equilibrium constant in terms of partial pressure. Then you have to write partial pressure P. In Kc, all these are expresses the concentration by molar concentration. Okay, active masses are expressed in terms of molar concentration. When the reactant and product are gaseous, you can also express their active mass by partial pressure like Pc to the power C into Pd to the power D divided by Pa to the power A into Pb to the power B. Okay, like this. This is the expression for Kp. When the active masses are expressed in terms of partial pressure, active masses of reactant and product, then the equilibrium constant is known as Kp. Okay, so Kc, Kp, these are expression for equilibrium constant. Kc is when the active masses of reactant and product are expressed in terms of molar concentration, and this is Kc. And when the active masses of reactant and product are expressed in terms of partial pressure, then it is known as Kp. Okay. Here it is also given reaction of H2 plus I2 to Hi. For this reaction, Kp is equal to Kp is equal to Phi divided by Phi square divided by Ph2 into Pi2. Okay, where Phi, Ph2, Pi2, these are partial pressure. Mm. So for this reaction, gaseous reaction, small a capital A plus small b capital B, gases written within within bracket, G means gaseous state. Okay, C G, within bracket G, D to within bracket G. All the this indicates that is the reactant and products are gaseous. So relation for Kp is equal to Pc to the power C into Pd to the power D divided by Pa to the power A into Pb to the power D, Pb to the power B. Okay. Now see relation between Kp and Kc. What is the relation between Kp and Kc? Equilibrium constant at constant pressure and equilibrium constant at constant uh, equilibrium pressure. Equilibrium constant in terms of partial pressure and in terms of molar concentration. Okay, so relation to given. What is the relation between Kp and Kc? The relation between Kp and Kc is Kp is equal to Kc into RT to the power delta n. Remember that. So the relation between Kp and Kc is Kp is equal to Kc into RT to the power delta n, where delta n is the change in mole number of gaseous reactant and product. Okay, Kp is equal to Kc into RT to the power delta n. So for reaction H2 plus I2 implies 2Hi. For this reaction, 1 mole hydrogen, 1 mole iodine gas react together to form 2 mole Hi. At equilibrium, what is the delta n? Delta n is equal to 2 mole Hi, so 2 minus 1 mole hydrogen plus 1 mole iodine. So 2 minus 2 0. For this reaction, Kp is equal to Kc. Okay, H2 plus I2 implies 2Hi. Okay, for the reaction N2 plus 3H2 implies 2NH3. For this reaction N2 plus 3H2 implies 2NH3. 1 mole nitrogen react with 3 mole hydrogen gas implies 2 mole ammonia gas. So the change in mole number of gaseous reactant and product delta Ng is equal to 2 mole ammonia minus 1 mole nitrogen plus 3 mole hydrogen. So the delta Ng is equal to minus 2. Okay, so for this reaction Kp is equal to, for this reaction Kp is equal to Kc into RT to the power minus 2. Okay, this is the relation. Okay, one more reaction is given. We have to write this for this reaction. What is the relation between Kp and Kc? Okay, so you have to practice how to write relation for Kp and Kc. in different chemical process, reversible chemical process. Okay. Now characteristic of equilibrium constant is given. Next I'll discuss about this. Okay, thank you students.